So it's my great pleasure to say welcome to everyone to this week's CCNB seminar talk by Philip Corlett from Yale University in the US. So we are very happy to have you here. In the last semester and in this semester, we had some focus in the seminar series on predictive processing in the brain. And so I was suggesting to invite you for this semester as I'm following your work for quite some years. I find it very fascinating where there's this focus in your research to explain specifically hallucinations and delusions within the framework of predictive coding and predictive processes in general. And maybe we will hear also about this work. I was just telling earlier about this very interesting study to find also healthy classified people to have regularly experiencing hallucinations, and then like this great idea to compare them against healthy controls and against people with psychosis and hallucinations. Beautiful design, which made it to a famous publication to then model those processes or the neural activity within the predictive coding framework and hierarchical processing. Very fascinating work, but also giving multiple overview articles explaining current hypotheses where in the cortical hierarchy the origins for hallucinations and for delusions might be, and how to embed this within the context of predictive coding. Also a great article I really enjoyed was about a model psychosis, also with NMDA mechanisms explained, and the history how different models to model such psychotic symptoms were used in the history of neuroscience to then like track the mechanisms and ultimately explain them, maybe in the predictive coding framework. So you've been working for longer time in Great Britain with Paul Fletcher at UCL, and now I didn't find exactly since when, but you have moved to be an associate professor of psychiatry now at Yale School of Medicine. So we are very happy to have you here, and I'm very excited about hearing your talk, and stage is yours.
Thank you very much. What a great introduction. I've been at Yale since 2009, and I was only meant to stay for a year, but I enjoyed it so much, and I've been there ever since. And what I'm going to share with you today is really a sort of continuation of that work that I started with Paul and his team during grad school. And then we've sort of developed it in some different directions whilst I've been at Yale. So I'm going to talk about hallucinations and delusions, which I define as the sort of profound departures from consensual reality that characterize serious mental illnesses like schizophrenia, but as I'll show you today, occur in a whole host of other illness contexts like neurological illnesses and strokes, but also in an attenuated form on a continuum in the general population. And as Timo mentioned, that's something that we are trying to sort of leverage to figure out what are the underlying mechanisms for having experiences and beliefs that don't conform to consensual reality, and how can we figure out what's pathological and perhaps what isn't, and what are the things therefore that we ought to aim our development of treatment mechanisms towards. I use the predictive processing framework, which is a way of understanding the mind and the brain. And that's led us to make some sort of interesting, kind of challenging observations that the accounts that we have for delusions to some extent run contradictory or orthogonal to the accounts that we have for hallucinations. And what I've been trying to do in the past few years is really figure out why that might be and come up with some hypotheses about how to put things back together again, because of course delusions and hallucinations do commonly co-occur. They're not perfectly correlated, but the data I'm going to show you today are somewhat challenging for that idea, and I'm going to give you an insight and some new data on how we're sort of putting things back together syndromically and thinking about how these things might coexist. So I'm going to talk to you about delusions, hallucinations, and paranoia, which is a sort of form fruit of persecutory delusions that runs through the general population. And what I'm going to show you is that delusions relate to aberrant prediction error signaling, hallucinations relate to how we apply our prior beliefs to inferences, and that those beliefs are too strong in the case of hallucinations. And I'm going to show you that paranoia relates to a belief about volatility, which gives us some clues about how to put everything back together. And I'm really fond of this framework from David Marr, which says that whenever we think about a task that the brain might be computing to achieve, we have to think about what exactly are the goals that the brain is trying to solve, what representations are being implemented and manipulated to try and solve those goals, and how are they being implemented in the neural circuits in our brains. And for the purposes of this talk, what I'm going to suggest is that we have brains, and to some extent bodies too, to minimize our surprise about the world and make better predictions about what's going to happen to us next. That algorithm is something along the lines of Bayes' theorem, or some sort of approximation towards Bayes' theorem, where we have some hypothesis or a generative model of the data that are incident upon us, and we compare the actual inputs to the predictions of that model and make inferences that are driven by the relative precision of our model and the data. And that gives us situations wherein we can make inferences that are weighted towards what we thought would happen, or indeed away from it, which might be an impetus toward belief updating and perhaps delusion formation. And through a whole host of studies from our lab, and also a meta-analysis of all studies of prediction error that have ever been published with fMRI, we've honed in on a sort of general purpose circuit that incorporates the striatum, the anterior insula, and the VTA, as well as more specific or domain-specific circuits that handle visual predictions, social predictions perhaps, and other types of predictions too. And I'll get into that towards the end. And really the point is that these layers aren't independent of one another, despite what some sort of ultra-cognitive neuropsychologists might want you to believe. I think that the algorithms that we propose and the computational goals that we think the brain might be working towards ought to be constrained by and influenced by the data that we gather from the brain. So I think there should be sort of strong exchange between these layers, which is actually something that David Marr believed in too, despite his quote about feathers and birds and flying. And there are all these sort of broader implications too. So if you're not particularly interested or excited about delusions and hallucinations, I think the work in our lab really has something to say about bottom-up versus top-down processing. I've already mentioned these words modularity or encapsulation and domain generality. I think the work touches on issues around cognitive penetration, whether what we think might change what we perceive, whether or not we have a social brain that's dedicated towards social stuff in particular. I'd like to think that perhaps we don't, or at least that we can get a very long way in explaining these deeply social phenomena by only appealing to domain general mechanisms, and I'll show you some data about that too. And I think it gives rise to thoughts about the biopsychosocial model in psychiatry and how we might think about those different pillars. And it would be no surprise for you to hear that I think that those things are inappropriately siloed, and that they lean on and constrain and conform one another. Here's our definition of delusions: fixed false beliefs that aren't amenable to change in light of contradictory evidence. Here's an example of what we might call the Capgras delusion. So a 74-year-old housewife who believes her husband has been replaced by another unrelated man, and she refuses to sleep in the same room as the imposter. She locks herself in her room, and she asks her son for a gun to protect her from this imposter. Now, I want to be very clear that patients with delusions don't always act on their delusional beliefs, and people with psychosis are about 14 times more likely to be the victims rather than the perpetrators of violence. But nevertheless, delusions and hallucinations can sometimes quite tragically motivate people's actions towards themselves and towards other people too, which I think is a real impetus for us to try and understand them better. Here's one way of trying to understand. So this is a sort of meta-analysis of all of the cases of new onset delusions that have happened after some kind of brain damage that have been reported in the literature. And what I'm showing you here are summaries of those cases, whether or not the person woke up from their brain damage incident and entertained a monothematic delusion, like their loved ones having been replaced by imposters. And what I'm showing you is that people often have damage to frontal cortex, parietal cortex, temporal cortices, white matter, subcortical structures, occipital structures in the right hemisphere and on the left. And what I've done here is connect two particular structures with a line if they're damaged at the same time in the same patient. And so the lines are thicker the more commonly two structures are co-damaged at the same time in the same person. And what you can see, I think, is that the right hemisphere is undoubtedly much more important, but not uniquely so, relative to the left in terms of damage giving rise to these delusional beliefs. And the frontal cortex seems to be kind of a hub. So right frontal cortex seems to be particularly important as a locus of damage for new onset delusional beliefs. But I find this kind of explanation not really an explanation and somewhat disappointing. And so what we've been trying to do in the lab is put some, I guess, psychological meat onto these neurobiological bones and really try and understand what these regions might be doing in generating these delusional beliefs. And here we turn to a really basic kind of reductionist approach to what causal belief formation might be. In humans and other animals, we're inspired by Pavlovian conditioning, which is the observation by Ivan Pavlov that a ticking metronome pre-exposed to a dog doesn't have any particular consequences and doesn't produce a particularly coherent response. However, if that metronome is paired with some tasty food reward, like this delicious steak, the animal will salivate in response to the steak initially. However, after time and repeated pairings of steak with metronome, the animal will start to salivate in anticipation of the delivery of the steak. So there's a sort of predictive process in play here. And we think that humans might learn causal relationships between causes and effects in exactly the same way as these conditioned responses come to be associated with these CS cues. The theory that we invoke really developed in the 1970s at Yale by two psychologists, Bob Rescorla and Alan Wagner, is this Rescorla and Wagner learning rule, wherein the term in parentheses, the prediction error, the mismatch between what you expect given all the cues that you've been presented with and what you actually experience, is what drives new learning. It's really an overly mathematical way of saying we learn from our mistakes, and we learn most when those mistakes are largest. And in a really beautiful review of how prediction errors might be instantiated in the brain in the year 2000, Wolfram Schultz and Tony Dickinson said, prediction error relates to the very essence of learning. No learning occurs when outcomes are perfectly predicted. And in a nutshell, our theory of delusions is that people form causal beliefs driven by aberrant prediction error signals that are happening when they really ought not to, and that's causing them to attend to and learn about things that they really ought not to, and that the rest of us tend to ignore or downweight. Here's how we access that in the lab. So we ask people to imagine they're an allergist. We show them foods on each trial that a person has eaten, and then the outcome of those foods, whether or not they have an allergic reaction. And the task for the participant is to make a prediction when the food appears on the screen, whether or not they think this person will have an allergy. Obviously, at first you have to guess, but as you see more and more repetitions, you tend to learn which foods cause allergies and which ones don't. So in this case, he eats hamburger and he suffers an allergic response. And every time you see hamburger, you see allergy. Hamburger, allergy. You learn this alongside a whole host of other control cues that are balanced for novelty and familiarity. And then I bring you into a second stage of learning where that thing that you've learned to asymptote, the hamburger causes the allergy, is paired with a novel food that you haven't seen before and that you don't have particular preconceptions about. And you see that this meal causes an allergy of exactly the same magnitude. And the question is, what do you learn about that novel food? Do you learn anything at all? Do you attend to it even? And this is an example of a phenomenon called Kamin blocking, which was reported in rats in the 1960s and 70s. It's now been replicated across a whole host of species. And the idea here is, if we're right, and that prediction errors are driving patients with psychosis to learn about things that they shouldn't, then they might learn inappropriately about this new food. This is what we see in control participants. They have a nice, strong prediction that the cue that they've seen paired with allergy very frequently causes the allergic reaction, and they're kind of ambivalent about that novel food that's been added in, the one that's been subject to blocking. However, if they're a person who's currently experiencing a psychotic episode in the emergency room, they play our game, and important things feel different, and different things feel important. They give too much causal significance to that novel food, and perhaps some behavioral evidence that aberrant prediction errors are driving them to come to that conclusion. We can also track prediction error signals in the brain. This is just a little overlay of all of the initial studies that we did of causal belief formation in the context of this food allergy task and similarly structured tasks. Whenever you see an outcome, not necessarily rewarding or punishing, but an outcome that you weren't expecting, we see a nice robust signal in right dorsolateral prefrontal cortex in healthy volunteers. And we see the same thing here, right? So if we show the blocked cue causing the allergy, you see a nice robust response in right dorsolateral prefrontal cortex. And if we show the blocking prediction coming true, that region of the brain is not particularly interested. However, much like our behavioral data, if you're a patient with first episode psychosis, you don't show enough of a response to truly surprising events, and you show too much of a response to events that ought to be highly predictable or run-of-the-mill. And we can summarize that effect by looking at the height, difference in height of these two bars. And what we see is, if your brain response to our task involves too much responding to run-of-the-mill predictable events, the difference in the height of those two bars is smaller, and you have more severe delusional beliefs, even taking into account hallucinations, negative symptoms, and all sorts of other confounding factors. This does seem to be a very specific relationship between the inappropriate presence of this prediction error signal and the severity of the delusions that people report. We can also model and replicate this with ketamine. Before it had its new life as a miraculous antidepressant, we were using it to transiently and reversibly model psychosis-like experiences in healthy people. Here's an example. Every time I left the room, they thought another person dressed in my clothes was coming back in, doing my job, a little older in age and weighing a bit more. Now, both of those things have happened since I moved to Yale, but not quite on that time scale. But you can see it has some of the flavor of the Capgras delusion, right? We're not close relatives, we're not married by any stretch of the imagination, but they are sort of misidentifying me. When we give people placebo, we see our typical prediction error response in right DLPFC to events that are surprising, not so much to the control events that are highly predictable. And that's not the case on ketamine. Just like first episode psychosis, important things feel different, so you're not as appropriately surprised as you should be, and different things feel important. Control or predictable events seem more surprising than they ought to be. And again, if we look at the difference in the height of these two bars on an individual by individual basis, we see again there's a correlation between aberrant perceptual salience and sort of delusion-like percepts on a high dose of ketamine. So starting to think that conversations are going on behind your back, or that there's more going on than the experiment because of events that are happening to you in the experimental context. The more that people have those delusion-like ideas, the more inappropriately they engage DLPFC whilst they were on ketamine. As I mentioned, these unusual beliefs that are sort of delusion-like are becoming increasingly common. I believe 60% of Americans believe at least one conspiracy theory. I'm sure we're going to hear about that a lot more tomorrow as the midterm elections take place. Depending on the outcome, they'll be coming from different factions. It nevertheless, I think, affords an opportunity to kind of study delusion-like ideas on this continuum, even in healthy people. And we do that with something called the Peters Delusion Inventory, which was developed by Emmanuel Peters. It basically takes a number of different delusion-like ideas, and if you endorse one of them, say, do your thoughts feel alien to you in some way, then you're asked Follow-up questions: how distressing do you find it? How preoccupied are you by it? And how convinced are you that it's true? And the bottom line is that you can find people out in the world who are as convinced and preoccupied, but they're very rarely as distressed as patients with delusions about these ideas that they're entertaining and endorsing. And so what we did was have people, healthy controls, rate the degree of distress with which they hold their delusional beliefs, and then correlate that distress with their prediction error brain response to our task. And just like on ketamine, just like in first episode psychosis, if you're a control who holds your delusion-like beliefs in a more patient-like way, your brain responds to our task in a more patient-like way, i.e. there's a smaller difference between responses to things that should be surprising and responses to things that really ought not to be surprising, consistent with the idea that you're evincing aberrant prediction error signaling in your brain. So, first third of my talk, delusions involve aberrant prediction errors. I turn to hallucinations now, which are percepts without an external stimulus, occurring in a conscious and awake state and having the qualities of real perception. You can quibble about this definition. It doesn't really encompass hypnagogic and hypnopompic hallucinations that happen when people are falling asleep and waking up. But nevertheless, we're going to try and analyze hallucinations in the same way as we did delusions. This is some data that I'm very fond of from the late Ralph Hoffman and Michelle Hampson, who's still here at Yale, looking at symptom capture during hallucinations in patients with schizophrenia. So you basically ask the participants to just push a button to report when they're hearing a voice in their head. And that is what you can see in this column here at time 0. This is the snapshot of brain activity when you push the button. And you can see some kind of interesting things here. This is time along the bottom, and 3 seconds before they push the button, there's all kinds of interesting activations and deactivations going on cortically. And then up to 4.5 seconds after they push the button, the regions of the striatum and the midbrain are coming online. These are the regions that are richly innervated with dopamine neurons. I think that's where the drugs that we use to treat these symptoms actually bind. And so you can see that they're not actually engaged until long after they've had the voice experience, which leads me to wonder whether when we're treating with these compounds, we're not actually addressing the things that are going on cortically that are sort of fermenting and giving rise to the experience. What we might be doing is modulating people's attributions after the fact, once they've had the experience, which is still fine. These are great interventions. They help people immensely. But wouldn't it be nice to kind of get really down to the core mechanisms and address the pathophysiology more directly? And the way we're going to do that is, again, through Pavlovian conditioning, now not between causes and effects per se, but actually between sensory-sensory associations. So there's a long history in perceptual psychology of using these predictive associations, in this case between the bell and the metronome, as setting up sort of perceptual expectations that lead people to draw particular inferences about what's going on in the world around them and within their own bodies too. Here's an example. So this is a rotating hollow mask of Charlie Chaplin's face. And as you start to see the inside of the mask, this is a video from the late Richard Gregory. As you start to see the inside, something unusual is going to happen. So around about kind of now, it's going to seem to you as though the mask switched direction of rotation. Of course it didn't, but in order for your brain to make sense of the various patterns of light that are incident on your retina and draw inferences about how light falls onto convex versus concave objects, the best way that your brain can come up with to make all of that stuff make sense in light of your prior knowledge that light falls on things from above, for example, you come to the conclusion that the direction switched rather than that you were looking at the inside of a hollow mask, which is not a common experience for you. We think that hallucinations work in the same way. I'm going to show you some data to that end. So in a nutshell here, we think that hallucinations are very strong prior beliefs about perceptual relationships that are so strong that they cut new percepts out of whole cloth, even in the absence of sensory inputs. Here's an example in the auditory domain. I'm not sure that this works particularly well through Zoom, but let's give it a try. So you hear a sort of series of bells and whistles and clicks, I'm going to play you a sentence now.
The camel was kept in a cage at the zoo.
And now if I replay you the original stimulus, you can't, I think, unhear now the camel was kept in a cage at the zoo, even in that degraded stimulus. And this is an example of sine wave speech. It was developed at Yale in the 1980s. They were trying to find how much signal they could take out of speech to render it unintelligible. And they found this kind of interesting effect wherein the template stimuli actually gave context to create an inference about what those kind of previously unintelligible signals were actually conveying. A prior on the content of the speech, if you like.
The camel was kept in a cage at the zoo.
What we know from work with people who hear voices in their heads, this is from Ben Alderson-Day at Hearing the Voice in Durham, is that people who hear voices actually detect the speech in the sine wave stimuli even before you tell them that there's any speech to detect. They can actually even detect particular words in the content. So some idea that they may have a strong prior that there's speech out there in the world, and that allows them to resolve these noisy signals where there is actually speech, but perhaps causes them to infer that speech is present even when there isn't any to be perceived. And this fits with a sort of model along the lines of what I outlined in the beginning of my talk, that we are making inferences to the best explanation for what would have to be out there in the world to make incident data make sense to us. This is the predictive processing model that began with people like Hermann von Helmholtz many, many years ago now. And it looks from the work of people like Carl Friston and others that something like this kind of predictive processing calculation is what's going on in our brains, by which I mean hypotheses are conveyed from the top down across cortical hierarchies. Any information that deviates from those hypotheses creates a prediction error, which is sometimes communicated bottom up, depending on the relative precisions of our prediction errors and prior beliefs. And those things are encoded in different hierarchical systems in our brains by different neuromodulatory neurotransmitters like dopamine, acetylcholine, and serotonin. All of the things that are involved in treating many of the symptoms of serious mental illness, but also all things that get engaged when we make interventions like giving psychedelic drugs that give rise to delusion-like and hallucination-like experiences. And that leads people to make these claims that drive philosophers and cognitive neuroscientists somewhat crazy, like all perception is controlled hallucination, or my favorite from Anil Seth, we're all hallucinating all of the time, and when we agree on the content of the hallucination, we call it reality. I think what the point of these sorts of statements is to make the case that perception is much more constructed and constrained by our past experiences relative to being a sort of passive input from the environment on a moment-by-moment basis. And I'm really fond of this quote from Pavlov himself, who said that what the genius Helmholtz, who kind of came up with this unconscious inference idea, was referring to is the mechanism of the conditioned reflex. So that's what we set out to try and test in the lab. Here's another example. About 50 to 60% of people polled on Twitter thought that they could hear a loud bang every time the pylon was hitting the floor, right? And so the expectation that loud noises follow large things colliding with hard objects leads people to infer that there must be a sound happening at the time of this GIF, contingent on the movement of the camera too. This is work that I undertook with Al Powers, who's now a faculty member. He was a trainee in the psychiatry department at the time. And we really tried to follow up on ideas that have been forming and fermenting at Yale since the 1890s, that there are these sort of sensory hallucinations that we can set up with people in the lab that lead to illusory and hallucinatory type experiences. We took a particular example from the 1940s that involved audio-visual conditioning. And what we do first is bring people into the scanner and find the intensity of sounds we need to play them so that they can hear them over and above the noise of the scanner, which, as many of you know, is sort of like a jackhammer going off. And so we can find how loud, on an individual by individual basis, sounds need to be for them to detect those sounds 75% of the time, 50% of the time, 25% of the time, and of course we can just not play any sound sometimes too. So we know these sound intensities for each individual, and we're going to take them into a subsequent conditioning experiment where checkerboards are paired with sounds of varying intensity over and over again. And the key trials are what goes on in your brain when you report hearing a tone that we didn't present you with, conditional on the presentation of that checkerboard. And we use this pseudo-random design to get around challenges of sort of demand characteristics. So at the beginning of training, there's lots and lots of pairing of above threshold tones with the checkerboards. But over time, there's more and more opportunity to make conditioned hallucination responses. So basically at the beginning, there's lots of reinforcement, but then extinction should kick in and people should realize that we're actually not playing them the tones as much. And we can test then the strength of what they've learned in how resistant it is to extinction. And we do this in 4 different groups of people, which Timo briefly kindly introduced for me. So we have a group of people who have a psychotic illness and hear voices every day. Those are our hallucinating patients. We have a group of patients who don't hallucinate but have the same diagnosis, so they have delusions and negative symptoms and they're medicated and everything else. Then we have a group of people who have neither a diagnosed illness nor voice hearing. And then there's this interesting group of people in blue who I'd be happy to talk about in more detail later. They believe that they're psychic. I don't agree. I agree that they're having experiences of voices in their heads, and I can talk to you about that more. But they don't meet diagnostic criteria for schizophrenia because these voice hearing experiences have not impaired their function. They don't seem to come along with various of the other kind of accessory symptoms that seem to be important for having a diagnosis. They're not in need of care, and so we call them non-clinical voice hearers. So the question is, who amongst these 4 different groups of people are susceptible to conditioned hallucinations in our task? And the answer is people who hallucinate in their everyday lives. So if you're a hallucinator, either a patient who hears voices or a psychic participant, you're about 10 times more likely to report the effect behaviorally in the scanner. Everybody gets it a little bit, so that the non-hallucinating controls and the non-hallucinating patients do show some conditioned hallucinations, but it's precipitously more frequent in people who hear voices in their heads, regardless of their clinical status. That's particularly the case below thresholds when the groups really seem to move apart. So perhaps when perceptual uncertainty increases, they rely much more on their prior beliefs. And that's what we're going to try and test with computational modeling a little bit later. The more you hear voices outside of the lab and the scanner, the more likely you are to hear tones that we didn't present you in the scanner. We were also able in that initial thresholding period to define regions of the brain whose activity waxed and waned with the intensity of the tones during that thresholding procedure. And as a nice internal kind of sanity check, that was regions of the superior temporal sulcus. We can take those regions and create a mask and look at what happens in our subsequent conditioned hallucination training when people report tones that we didn't play them. And pleasingly, without wanting to engage in too much reverse inference, when people report hearing tones that we didn't present them, it's exactly those tone-sensitive regions that seem to be engaged. And this was really satisfying to us and fits with a sort of literature, even dating back to Wilder Penfield, who, when he stimulated parts of this superior temporal region, the participants reported hearing buzzing and sort of tone-like stimuli. So we think they're actually having an experience when they report hearing these tones. Obviously, it's not definitive evidence, but certainly consistent with the idea. Then when we look outside of those tone-sensitive regions, we see a whole panoply of regions of the brain that are responding when people report hearing tones that we didn't present them, including regions of the anterior insular cortex, the striatum, the thalamus, the midbrain, and the anterior cingulate, all regions that are typically involved in learning, decision-making, and making sort of difficult perceptual decisions. Really nice overlap, though, between the set of regions that are engaged when people are reporting hearing a voice and pushing the button and the circuit that we're engaging with our task. So these are data from a meta-analysis by my colleague and friend Renaud Jadry of all of the studies that have been reported in patients with schizophrenia pushing a button to report that they're currently hearing a voice in the scanner, what's going on in their brains. And this is the overlap between those results and our data of people reporting tones that we didn't present them with. So there's a really nice overlap. The same circuit seems to be brought online by our task that also seems to be engaged when people are reporting voice hearing in the scanner. We wanted to try and unpack what those regions might be doing, and we turned to computational modeling here using the hierarchical Gaussian filter approach, which looks very complicated. It's actually very simple. Imagine that there are 3 layers of evolving belief about what might be going on in the task. Are tones occurring in the task? Are those tones being predicted by the checkerboards? And are those tone checkerboard associations changing and evolving over time as the contingencies are changing? We can estimate those layers of belief by looking at the participants' behavioral responses, and we can kind of glue those different layers of belief together with different learning rate parameters that govern how sensitive people might be to the volatility and changing circumstances. And particularly important for what we're going to show you, we added this extra parameter, which seemed to be really key, of how strongly people weight their past experience in the task of the tone checkerboard association on their current inference on a particular trial. All of those things are squished together and pushed through a response function. It's basically a sigmoid that has a temperature that we can also assess, which sort of looks at how biased people might be. When we fit this model to our data and then use the estimated parameters to simulate behavioral responses, we see that we get a really nice fit, and it recapitulates that pattern of responses that we saw, wherein patients and voice hearers, now their estimated parameters, also produce behavior that's consistent with them overweighting their prior beliefs, particularly at below threshold intensity. So we think we've got the right model. We're not overfitting, and it's recreating many of the key features of our data. When we look at the inverse temperature, it's no different between the groups. So it's not that the patients or the voice hearers are just saying yes to everything. They do have a stronger prior weighting as estimated from their behavior. Voice hearers of both clinical and non-clinical ilk have strong prior beliefs relative to non-voice hearing controls and patient participants. And that's manifest as a stronger belief in the voice hearing groups that tones are occurring and that those tones are being predicted by the checkerboard. However, in a really nice, I think, double dissociation, patients with psychosis, regardless of their voice hearing status, are less sensitive to that volatility that we introduced. So they kind of stick with their beliefs and don't seem to update their beliefs in light of evolving evidence. Not so in the controls or in the psychics. So voice hearers, both clinical and non-clinical, overweight their prior beliefs, and patients with or without hallucinations can't update their beliefs in light of evolving evidence. We've replicated this now in people at clinical high risk for psychosis. So these are people who aren't yet having schizophrenia, but nevertheless are starting to show some what we call prodromal signs or symptoms of being at risk for psychosis. These people show many, many more conditioned hallucinations. We think that the scanning might also be useful in that regard, right? Because we can look at the function of this hallucination relevant circuit before it started to produce hallucinations in people who are at risk. We've replicated this effect again in patients with schizophrenia now across a number of different sites. If you're somebody who hears voices, you're more likely to show conditioned hallucinations, and those conditioned hallucinations again correlate with the severity of hallucinations in your everyday life. This time, what we've done is not just fMRI, but also magnetic resonance spectroscopy across a number of different sites in the brain, so different voxels. It took quite a long time because you have to take these pictures in series. When we estimate the level of glutamate, what we find is that region of anterior insular cortex, which was sensitive to prior overweighting in our fMRI study, also seems to have a dearth of glutamate. And the lower the glutamate that you have in that region, the more likely you are to overweight your prior beliefs. So some evidence that hallucinations involve the overweighting of perceptual priors. perhaps something to do with the anterior insular cortex and the level of glutamate therein. I'm going to turn and talk to you in the last part of my talk now about paranoia, which is the belief that other people intend to harm you. We've explored paranoia in my lab alongside Jane Taylor, Steph Groman, and Erin Reed, who really drove this initial work by turning to probabilistic reversal learning, which is a task that we can study in humans, we can study it in rodents, we've got data in rats that I'm going to show you, we've now got data in mice, we also have data in monkeys of this exact same task. Whatever the organism is, you confront them with a choice between 3 different options for reward. In the case of humans, it's for points. In the case of animals, it's often for food reward. Basically, the challenge is to pick the best option to choose, and they're told, or they learn, that that best option can change over time. So you might start out picking the blue and get rewarded quite a lot of the time, but at some point that's going to change, and you might need to decide whether when you get a loss, is that a signification that the contingencies have switched, or is it just a run-of-the-mill probabilistic event? And what we find in healthy people and in patients who have lots of paranoia, there's lots of excessive switching between options even before, even after a win. So, which is a sort of irrational thing to do in this context, right? If you've just won, there's no reason to change what choice you're making. Highly paranoid people switch choices when they don't really need to. We've again fit this hierarchical Gaussian filter model to the behavioral data that we've gathered in this reversal learning task. This time, the lowest level is, did you win or lose? So not presence or absence of a tone now, but presence or absence of a win. The mid layer tracks your beliefs about the current values of the dex, the one that you're choosing and the other 2 that you didn't choose. And then the highest level of the model is, what do you believe about the changing statistics and the underlying probabilities of the dex, and how are you tracking that volatility? And that comes with a prior belief, which we can estimate. So essentially, how volatile do you think the task is going to be throughout? There are also some learning rates about how you actually learn from real volatility. And if that particular learning rate is lower, then you're slower to learn and update your beliefs in light of changing contexts. There are also some other learning rate parameters that govern how sensitive you are to surprises, either sort of punctate events or changing trends as the trials that you experience tend to evolve. And what you can see, I'm not going to go into details, but in an in-person experiment, in an online experiment with people who are reporting high and low levels of paranoia, and in a rodent experiment where animals are exposed to methamphetamine, which is itself a model for paranoia, the pattern of beliefs and behavioral parameters that we can estimate from the choices that the animals and the humans make is strikingly similar. They have stronger prior beliefs about volatility, but they're less able to learn appropriately from that volatility when it actually happens. Rather than just believe me that these things look similar, we've now engaged in a sort of hierarchical clustering analysis, which basically takes the data from these 3 experiments and tries to see, are there underlying patterns of parameter values that can confirm and sort of constrain different underlying groups of participants? And the answer is yes. There are 2 clusters of participants when we group our online studies, our patient studies, and our methamphetamine animal studies together. There's a group, cluster 1 in black, which is comprised mostly of methamphetamine-treated animals and high paranoia humans. And then there's cluster 2 in gray, which is the saline-treated animals and the low paranoia human participants. And just to kind of convince you that this isn't overfitting again, what we do is look at just half of the data at random on their own, and we see the same underlying pattern. Look at another half of the data that we didn't look at, again, the same underlying pattern. If we just exclude the rat data, we see the same underlying pattern. And if we only look at the rat data, we see the same underlying pattern. So we seem to believe that there's a construct in the house based on how people participate and play this game. Based on the pattern of erratic switching responses, we can infer that they're much more likely to be paranoid if they're a rat treated with methamphetamine or a human just engaging with the task. So people with paranoia behave as though the world is more volatile, but they're slower to learn appropriately from real changes that happen. And this fits, I think, with this really nice summary from Richard Hofstadter of the Paranoid Style in American Politics, where he talks about the paranoid spokesman seeing the fate of conspiracy in apocalyptic terms, trafficking in the birth and death of whole worlds and political orders, always manning the barricades and constantly living at a turning point. I think that's what we're detecting with this task, so that there may actually be a methamphetamine style in our rats. Now, people have lots of other ideas about where paranoia comes from. Some people have started to suggest that because paranoia is about other people, as are many other delusions and hallucinations, that perhaps some sort of module in our brains that handles social relationships might be particularly important and relevant to the presence of paranoia. And of course, there are people who sort of dispute this. There's an ongoing debate in the literature about whether we have an evolved domain-specific social module in our brains. I'm not so sure, but I'm going to show you some data that perhaps we don't have something like that, or at least we don't need to appeal to something like that in order to explain paranoia. So right before the start of the pandemic, we launched an experiment wherein we basically made social and non-social versions of the task. Instead of learning from decks of cards, you're learning from different collaborators that can make your points go up or your points go down. We can color them in exactly the same way, and we can arrange for exactly the same contingencies and contingency shifts. And we can see, is there a preferential relationship between paranoia and the social version of the task relative to the non-social one? And the answer is no. We see exactly the same pattern of results and associations between high and low paranoia as we see in our non-social version of the task. However, we were fortunate enough to be running this experiment as the pandemic descended, and we were able to track how people's behavior changed over time and over the different periods of the pandemic, from lockdown to sort of early reopening when we were being encouraged to venture out into the world. What we see is that paranoia increased precipitously, especially during lockdown, but then even more so during reopening into the world. That was particular to paranoia, so whilst depression and anxiety did go up, paranoia went up even further. And the way people interacted with and behaved on the game was constrained by the local policies that they were exposed to, both in terms of the vigor with which they were asked to lock down. Some people in some states in the US weren't allowed to leave their houses, for example. And at reopening, whether or not a mask mandate was imposed. So if you were in a place where there was a mask mandate, people tended to be more paranoid and to be engaging with the task in a much more erratic way. We can show that here using a difference in differences analysis from econometrics. If a mask mandate was imposed, people's paranoia and win switch behavior and volatility priors on our task all seemed to increase. And that was sort of surprising to us, and I think has been a puzzle throughout the pandemic, why these simple measures might be so difficult for people to follow. And the answer, we think, is that humans are conditional cooperators. They're happy to go along with the rules as long as they perceive everyone around them following those rules. And what I'm showing here is this multiple regression analysis wherein we show if there's a mask mandate and you're in a place where people typically follow the rules, but you perceive that people around you aren't following the rules, then paranoia and erratic behavior on our task increases. So there's sort of local cultural milieu and then rules that are imposed, and then whether or not those rules are being followed, all contributing through this very basic learning mechanism to how people are becoming more paranoid and interacting with our task. The same was also true for people's conspiracy beliefs about the vaccine and the provenance of COVID. So more paranoid people also tended to believe more in the QAnon conspiracy, and QAnon belief correlated with volatility beliefs and win switch rates on the task too. Interestingly, people believed that the task was sabotaging them whether or not there was a social frame. So we're coming back to and now trying to unpack those beliefs. It could be, rather than nothing being social here, everything's social, and they're even approaching this very non-social task with a view, with a much more social view. We don't think that's true. We think our animal data tend to challenge that sort of assertion, but in follow-up work, we're really trying to figure that out. So paranoia involves strong prior beliefs about volatility and change. I'm sensitive that we're sort of running out of time for discussion, so I'm going to sort of speed through how we're going to piece it all back together to make sure we've got enough time to chat. So what I've shown you so far, delusions relate to weak beliefs and too much surprise, hallucinations to very strong prior beliefs, perhaps in a different domain, perceptual rather than conceptual, and that paranoia relates to switching of beliefs, perhaps related to this overall belief about how things are going to change erratically. Now, we're going to turn, and the way I'm going to hopefully put all this back together, to the actual contents of the symptoms. So what you can see here is the general kind of three-factor solution, wherein delusions and hallucinations form one cloud, thought disorder, like having tangential speech and having your ideas jump from topic to topic, form a separate coherent cloud, and then negative symptoms, all of those sort of problems with motivation and volition, form a separate cloud. Now, what I'm going to show you and what I'm going to appeal to kind of put all this information back together is that the content of your delusions and hallucinations really matters. So whilst statistically delusions and hallucinations tend to co-occur, they don't always with the same contents. Right? So you can see that referential, religious, and grandiose beliefs tend to cluster up at this end of the overall cloud, and that auditory hallucinations and command hallucinations and delusions of control and passivity cluster together at this end. And in the middle, these are delusions and hallucinations about having poor boundaries, right? Being porous, having the contents of your minds broadcast out loud, or having sort of somatic delusions and hallucinations, wherein the phenomenology is not necessarily belief-like and not necessarily percept-like. What I'm going to suggest is that the two accounts of delusions and hallucinations I've shown you really fall down along these phenomenological lines. Here I'm showing you data where we've replicated those initial observations in all of the publicly available data. There are certain delusions that are very, very rarely associated with the presence of hallucinations, others that are more commonly, right? So having somatic hallucinations tends to correlate with having thought broadcast and delusions of control, not so much grandiosity and jealousy. If you have lots of passivity delusions, you're also much more likely to show conditioned hallucinations in our task, regardless of whether you're currently hallucinating. And the severity of your passivity delusions correlates with the severity of your conditioned hallucinations in our task. So some suggestion that what's going on with passivity and auditory verbal hallucinations may be related to one another. And when we look at how hallucinating and non-hallucinating patients behave on our task, the non-hallucinators are the ones that win switch a lot. And the hallucinators are the ones who show lots of conditioned hallucinations. So there may be different behavioral patterns that we see across these two tasks now, forming sort of consistent or coherent underlying subpopulations of participants. So you start with a prediction error. If you use that prediction error to update your prior about how volatile the world is, then maybe you get paranoia and sort of grandiosity and referential delusions. But you can also reconcile prediction errors by changing your overall perceptual beliefs and cancelling those prediction errors out. If you do that, you get passivity delusions and hallucinations. So I'm going to stop there. This is what I think I've told you, and I'm excited to have a discussion. Thank you.